All right, optimization part 4. A man wishes to get from an initial point on the shore of a circular lake with radius 1 mile to a point on the shore directly opposite on the other end of the diameter. He plans to swim from the initial point to another point on the shore and then walk along the shore to the terminal point. And then it lists how fast he can swim and how fast he can walk, and we'd like to know what are the minimum and maximum times for the trip. So what I'm about to do is pretty similar to what everybody else does when they try to solve these things. We usually label this here something like, choose the right, like B for the beginning and then E for the end, meaning they're on a diameter. This is a total of 2 miles across here. And then what he's going to do is he's going to take some of this and swim to a certain point on the shore, and then from there on out he's going to walk. So we've got swimming part, and then we have the walking part. So of all the things I've ever seen, ways to solve this, they always come down to something like measuring the angle at which he starts. So here, let me write the lake in here. Lake. We got a total of 2 miles, but I'll put a dot hopefully in the middle here. It tells us we got 1 mile and 1 mile. That's the radius. And then I'll let theta be the angle that he aims to swim for. So here's what we have then. If theta is 0, so if theta equals 0, that means he swam the whole time. I gotta make that more reasonable. So I'll say swim only, and if theta equals pi over 2, 90 degrees, that means he'll start straight up, which means he'll walk only. So what I've got to do is I have how fast he's able to do these things, but I got to make use of a very fundamental formula. I've put a bunch of these here because I don't know how many of these circles I'm going to need near the end, because I'm going to draw a bunch of different pictures. But one thing that you should keep in mind any time you have a constant velocity or constant rate, that's probably the better way of looking at it. You have the formula d equals rate times time. What that means is that the amount of time you spend will be d over r. So these are r's that I'm given for these things, and the distances I need to figure out. And if I have that, then I'll have the total time. So let's start with the distances, and let's start with this distance, the swimming distance. So I'm going to make, there's his swim. And then from the center, I don't want to make this seem like this is made up where it's going to be a 90-degree angle. That's not necessarily true at all. So I'll make it a little more exaggerated. Say he swims up to here. And this is the distance here. So this was the swimming distance. And we're told that angle there is theta. All right, the key to getting this distance here then, remember this side is 1, is to complete the triangle like so. And notice that this length is also 1. So since this theta subtends, or this side subtends that angle theta, one of the basic theorems of triangles is that since this side length is the same, this will be the same theta up here. So I'll put it up here also. And then what do we have left? Well, there's pi, a total of pi, for the angles add up to pi inside of there, and I take away 2 theta, and the angle that's left in here is pi minus 2 theta. So I'm able to get D using something called the rule of cosines, or the law of, I think it's called the law of cosines, not the rule, the law of cosines. And let's go ahead and do that one, the law. What it says is this length here, it's a generalization of the Pythagorean theorem. Basically, it says this length here, d squared, equals this side length squared plus this side length squared. So you can see where it's related to the Pythagorean theorem. But then we subtract 2 times the length of this side times the length of this side times the cosine of the angle, which is pi minus 2 theta, the subtended angle. All right, and I'll simplify it and solve for D. And while I'm here, let me move this guy out of the way. I don't think it's going to be helpful to have it right there while I'm doing this. This equals D squared equals 1 plus 1 minus 2. 2 minus 2 cosine of pi minus 2 theta. And then D equals the square root of 2 minus 2 cosine of pi minus 2 theta. I think what might not be a bad idea to do is put a little sub s here. Why am I putting this s in here? Well, this is the distance that he swims. And then I'll look at the distance that he walks, and I'll call it d sub w. So that's his swimming distance. So then what is his swimming time? Well, if I call t sub s his swimming time, that's equal to d sub s over his swimming rate. If you don't mind, I use r sub s for the swimming rate. Well, here's the formula for the distance. Square root of 2 minus 2 cosine of pi minus 2 theta. And while he's swimming, it said the rate was 2 miles per hour. So in fact, if you really want to think about it, the time spent swimming is a function of theta. Okay, so that takes care of, this is the time for swimming. All right, that takes care of this portion of it, the swimming portion of it. Then for the rest of the way, he's going to walk. So let me draw a new picture with the walking part. I'll go like I did before. I'll put a dot in the center. This is supposed to be where the center of the circle is. And I'll try to mimic what I saw over there. So now this is going to be d sub w, the walking distance. And notice that that is an arc length. Now, here's another thing too. Notice right here, this angle is pi minus 2 theta, but it sits on this angle plus this angle here add up to be pi, so that forces this angle to be 2 theta. That makes finding this distance very simple, because in any wedge shape like this, if you have any of a wedge shape, and the radius is r, and notice in our case the radius is 1, and you have theta in between. Let's call this the distance from that to that. Well, if you could do a whole circle, you have the circumference is 2 pi r. That means if you want the arc length, then it's going to be whatever the angle is, theta. In the case of going all the way around a circle, it's 2 pi. But imagine if you just stopped short and only went to theta, then replace the 2 pi by theta and replace the r by 1. So dw equals r theta. Well, my theta is actually 2 theta times the radius. This is the beauty of having theta in radians. You couldn't do this if this were degrees. Radians can work as both an angle and a length. Well, in fact, the radius is 1, they do in fact, the arc length is actually equal to the angle in there. So there's my d sub w, and then what is going to be its total time. So let me call it t sub w equals the distance traveled divided by the walking rate, which is 2 theta divided by 4 miles per hour. And so that gives us theta over 2. So the total amount of time then is just going to end up being the time spent swimming plus the time spent walking. So total time t equals t sub s plus t sub w. Now I think I'm even going to go one step farther and call it a function of theta, because that'll be my variable theta. That's clearly what's going to be the thing that moves in this problem. The t sub s, let me go back and grab that. That was all this stuff. The square root of 2 minus 2 cosine of pi minus 2 theta all over 2 plus theta over 2. And first thing we should notice is what kind of an interval, if any, is theta forced to be in. And I think it's pretty obvious here. He's either going to swim all the way, walk all the way, or something in between, obviously. But my angle, the lowest it can possibly go, is 0, and that could possibly happen. He could swim the whole way, or if theta is pi over 2, he could walk the whole way. Those represent the endpoints. So what we have then is that 0 is less than or equal to theta is less than or equal to pi over 2. Remember what we do then when we have a closed and bounded interval is we try the endpoints and any critical numbers that occur within the interval, and then we just compare those. So let me take the derivative and set it equal to 0. All right, so this 2 I've pulled out front in the 1/2. Take this, the derivative of the square root is 1 over 2 times the square root. And let me increase all division bars and such. Now, according to the chain rule, you have to take the derivative of what's inside. Inside of here, the derivative inside of here, that 2 will disappear, but this negative 2 cos will become positive 2 sine. And then you're not done yet because there's still a function inside of here. The derivative of pi minus 2 theta is a negative 2. Don't have much room, but I don't need much for this. The derivative of theta over 2 is simply 1/2. Remember, theta is the variable in here. Now there's a bunch of things that I can simplify here. I can take this 2, for instance, and take it out of here. I can take at least the 2 that's here and take out that one. And so this leaves me with sine of pi minus 2 theta. Don't forget that negative. Can you imagine how painful it would be? You get a paperback and you notice that you missed that thing. So I'll put it out front so I hopefully do not forget it for the rest of the problem. Now we're supposed to be setting the derivative equal to 0, so I'll set this side equal to 0. And then I'll just add this chunk to the other side. And then next, I'm just going to cross multiply. Now hopefully you're playing along at home. Next, what seems obvious to do to me is to square both sides. That's sine squared now, so make sure you square that part of it too. Of course, on the right side, the square root just goes away and you get 2 minus 2 cosine of pi minus 2 theta. To make everything in terms of cosine of pi minus 2 theta, I'm going to rewrite the left side. Sine squared equals 1 minus cosine squared. Then let me just multiply out the left side. I'll get 4 minus 4 cosine squared of pi minus 2 theta equals 2 minus 2 cosine of pi minus 2 theta. And I'll gather everything to one side. So I guess I'll just take everything to the right side. So I'll have 0 equals 4 cosine squared pi minus 2 theta minus 2 cosine of pi minus 2 theta, and then I take 2, take away 4, minus 2. Now, a common trick here, you notice that I have the same kind of an unknown quantity appearing twice in here. A common thing to do is to allow some letter to stand in for these and then use a common algebraic method to try to solve the thing. So I think usually z is the letter used for this kind of stuff. I'm going to let z equal cosine of pi minus 2 theta. Put that off to the side. So my equation then becomes 0 equals 4z squared minus 2z minus 2, which is a standard quadratic equation. I'm going to divide 2 into both sides and get 0 equals 2z squared minus z minus 1. I happen to notice this factors beautifully. 0 equals 2z plus 1 times z minus 1. Of course, check this real quick. 2z times 2z, that's the 2z squared. Then I have, if I do the outer ones, I get negative 2z plus positive, so I get negative z, and it all works out. So this gives me the two solutions. Z equals negative 1/2, z equals 1. Now I can go back and replace z with my cosine expression. So I get cosine of pi minus 2 theta equals negative 1/2, and cosine of pi minus 2 theta equals 1. Well, keep in mind, I'm dealing in the first quadrant with my thetas, so as far as solving anything, since I have a 2 theta, the most I should probably venture out is up to pi, because then when I divide by 2 to solve for it, I'll be within 0 to pi over 2. So in the second quadrant, there is a solution for cosine of something equals negative 1/2. Cosine is negative 1/2 at 2 pi over 3. So you have pi minus 2 theta equals 2 pi over 3. And the same deal over here too. Don't say this stuff is equal to 2 pi. That won't do you any good. This occurs, the easiest place where this occurs is when cosine equals 1 when theta equals 0. So I'm going to set pi minus 2 theta equal to 0. It's so easy to solve, I can't wait. So you'll get theta equals pi over 2. This situation here does represent complete walking. Now let's see what happens here. We get negative 2 theta equals negative pi over 3. So theta equals pi over 6. I already considered this point anyways. That's an end point. So we just need to try theta equals 0, theta equals pi over 6, and theta equals pi over 2. And I need to do that into the formula for t. So let's find that. There it is. I'll go ahead and copy it. So all I have to do is really compare the three of these. Whichever one's the smallest is the absolute minimum time. Whichever one's the largest is the absolute maximum time. So start with t of 0. T of 0 equals the square root of 2 minus 2 cosine of pi minus 2 times 0. All of that over 2 plus 0 over 2, which equals, let's see what we have in here. Cosine of pi is negative 1, so I'm going to get 2 plus 2. I'll get 4 here. So I'll get 2 plus 2 times 1 over 2. This will equal 1. So that's 1 hour. Remember, this was measured in hours. That's 1 hour. And that represents swimming the entire time. Let's see if that makes sense. You have to go 2 miles because the radius was 1 mile. So, but you swam at 2 miles an hour. So that's right, 1 hour. I could have done that without all these things, but I guess it shows these calculations were valid then. T of pi over 6, and that's something between 0 and pi over 2. Remember, you had to kind of pick whatever your solution to be so that it works out in the interval that we're working in. That is the square root of 2 minus 2 cosine of pi minus 2 times pi over 6. All of that divided by 2 plus pi over 6 divided by 2. And that equals, let me see, pi minus pi over 3 is 2 pi over 3. Square root of 2 minus 2 cosine of 2 pi over 3 divided by 2 plus pi over 12. And then cosine of 2 pi over 3 is negative 1/2. So inside of this square root, I'll have 2 plus 1, or I'll have radical 3 over 2 plus pi over 12. And that's in hours. And I'll get let's go ahead and get an estimate for what that number actually is. Square root of 3 divided by 2 plus pi, which is above this button here, this caret button, divided by 12. And that's about 1.128 hours. So it's approximately 1.128 hours. So far, swimming the whole way is faster than going out there and then going the rest of the way. And now let's take a look at t of pi over 2. That equals the square root of 2 minus 2 cosine of pi minus 2 times pi over 2. All over 2 plus pi over 2 divided by 2. So inside of here, the 2's cancel. It looks like pi minus pi, so you'll have cosine of 0. Cosine of 0 is equal to 1. So I'll have 2 minus 2 times 1. I'll have 0 in the first spot, and the second spot will be pi over 4 hours. And I happen to know that's approximately 0.785 hours. So walking the entire distance is the fastest. So walking is fastest. And then the slowest time we got was the 1.128, swimming at an angle of pi over 6 was the slowest. The time for the fastest was pi over 4 hours, and the other one was about 1.128 hours. This is a pretty standard problem. I was going to just go from the description and see what you could do with it, but this type of problem is almost always done as an example in the book to show you how to set up, because I'm not sure many people would consider using an angle here as their first possible guess. Or some books start and they look at the angle from the center to that point. And you saw whatever the angle is here, and the angle that is in here, this is from the halfway or the radian center out, is twice the angle that was here. That's good to know. I mean, it's very helpful. There's a lot of problems that have stuff like that in them. Doesn't look like I needed that one, but I don't care. So I don't know how many of these examples I'm going to do, but definitely going to do at least all of the most popular ones that I know of.